section 6.3, which is volumes. Volumes by cylindrical shells. Last section we did volumes by discs or washers, depending on which sort of object we had. There may have been a triangle problem. We didn't have discs or washers in there. But now we're going to do shells. So, why? We already have a technique for finding the volume of a 3D object. The issue is some 3D objects aren't nice, and doing it the 6.2 way may give you like a really nasty integral that you don't want to integrate, or it's just ugly or pain or whatever. So this is another technique you can use when confronted with a 3D object to find its volume. So let's start with a basic recap. We have a cylinder. You all have taken geometry. How do we find the volume of a cylinder? Here, let me label some things for you. What do we have? We got a radius, a circle, and the cylinder has a height. So the volume of a volume. The cylinder is what?
The area of the base times the height.
Area of the base times the height. Absolutely. And in a cylinder, the base is a circle. And to find the area of the circle, it's pi r squared. Pi r round? Yeah, pi r squared. And then we multiply by the height, which in this case is h. Volume of cylinder, geometry, we know this, hopefully. But we're not dealing with strict cylinders, we're dealing with cylindrical shells. What does that mean? I brought a visual aid. Visual aid. So if this was a solid block, a solid cylinder, we would use this guy to find the volume. But it's not a solid cylinder, I need to put my coffee in it, right? So if we wanted to find the amount of ceramic material used to make this coffee cup, we would find the volume, excluding the handle, pretend that doesn't exist. We'll find the volume of the outside cylinder, and we'll subtract the volume of the inside cylinder. So, we have a shell. Let's see if I can draw a shell so it makes sense. Is the picture okay? So let's label some things. So we got the big outside cylinder, and we have the empty inside cylinder. So the volume of the shell is going to be the volume of the big cylinder minus the volume of the little cylinder. So let's label some dimensions here. We still have a height, h, and then we've got a radius of the little cylinder. I'm going to call it r sub 1. No, not 1. Let's use L, because it's the little one. And then we'll have the radius of the big cylinder, which I'm going to draw over here. I'm going to call it RB. So the volume of the big cylinder, just going to use this guy right here, right? Pi r, and then the r of the big cylinder is RB squared times h minus pi r squared L times h.
Does the little cylinder have the same height? Is it like the coffee magnet doesn't go through, so are we cutting all the way through here?
That is a really good question, and I was curious about that myself when I was reviewing this section. I gave the big cylinder and the little cylinder different heights, and I was like, wait, I can't make the calculus work. So what happens, just like when we introduced integration, we're going to make the big cylinder and the little cylinder get closer and closer and closer and closer together, right? So eventually they're going to have the same height anyway. And by giving them the same height instead of different heights, that would introduce some once we do our integration and take the limit, they get closer and closer together, the air disappears. It's a good question though. So what happens next? I see like terms, so I'm going to pull some things out, distributed law, you know. So we got a pi here and h here, pi here, h here, pi, h, and then we have the radius of the big one squared minus the radius of the little one squared. Is that familiar to anybody?
Can you just pull out the squared too?
Pull out the squared too. What do you mean?
Like couldn't we just write that as RB minus RL squared?
Like, put that up there?
Yeah.
Ah, no. That's not allowed. That's not allowed. Because, let's do a little side note here. So RB minus RL squared is equal to RB minus RL times RB minus RL. That's what squared means. And when we FOIL that all out, oh, FOIL, man, you guys. Okay. RB squared minus 2RB RL plus RL squared. So when we FOIL this guy out, we don't get this. So they aren't equal. But we are going to need FOIL. If you guys remember a formula, difference of squares, it's on your reference sheet. I encourage you to look it up on the inside of your book, or not the little pull-out in the back in the index, as I've pointed out to you many times, Appendix 1. So if we use difference of squares to factor this, we get pi h, we get RB plus RL times RB minus RL. That's how we factor the difference of squares. So this guy, what is that? It's the difference in the radius between the big one and the little one. Right? Delta R. Oh. Yeah? It's the difference in the R's. As I said earlier, we're going to do calculus, and we're going to make the things, the big one and the little one, get closer and closer and closer and closer together. So these guys are going to get closer and closer together. But before we do that, for our purposes, what we're going to do to make our formula nice is we want to look at the average of the big radius and the little radius. So that there's two things that we're adding up. We want the average, we divide by 2. So RB plus RL over 2. If I divide by 2 here, and I want this to be the same thing as this, I also have to multiply by 2. So 2 pi h times the average of the radiuses times the difference of the radiuses. Okay? If I wanted to find the volume of the shell. There's no integrals yet. Gotta get some integrals in here somewhere, guys. So what do? The main idea in calculus is we can't figure a big thing out, so we break it up into little parts, and then we figure out all the little parts, add them all up. So we want to take our little parts smaller and smaller and smaller. Does that sound like anything to you guys? No?
A limit?
Limit. Yeah. Yeah. Limit of what?
Cylinders?
Totally, right? Exactly. Okay, so I'm going to take all these guys. I'm going to add them up. This is just a representative shell. I'm going to find all the shells in our whole object and add up all their volumes. So I'm going to take the sum of all these shells, 2 pi h. Now I want to pause a moment and say my notation is a little sloppy. And if a professor walked in right now, he might be mad. So if you want a little bit more careful notation, please read your book. But I feel like it's a little bit scary, right? The notation in there with all the stars and the subscripts and stuff. So forgive me, please. And we have the average here. I'm just going to call that R. And then the change in R. I'm going to sum all of them up. And what I'm going to do is take the radius, make it as small as I possibly can, so I'm going to take the limit. The limit, delta R.
Alright, I have good news and bad news.
Time's up.
Time's up.